So the first one here is a little tough to visualize without a picture. So I'm going to start out by drawing a picture. We have a warehouse that is 48 feet by 64 feet. So I gotta make sure okay, we are getting audio, good. Well, and it's, without a picture, it's really tough to get to. So it has beams every 12 feet. The beams are going to run the long way. So that means they're going to run in this direction. So they're spaced every 12 feet in this direction. Now, I drew this out to, well, not to scale, but to the right amount there. But when we're looking at this, if I want to know how many beams are needed, hey, Gabe, I'll get you checked off here. To find the number of beams needed, the spacing is 12 foot, and we call it the run. That's the area or the length that needs to be covered by those 12-foot gaps. So this would be the run that we're looking at to cover with those beams, is 48 feet. If we just divide 48 divided by 12, we get 4. Well, that's not the number I have in the picture, because when we just divide the length by the spacing, it's going to give us either one extra or one less, depending on what our needs are. For these beams, we do not need one at the beginning because there's a wall there. We don't need one at the end. Because we don't need beams at either end, this is one more than we need. So we subtract one from that, means we're going to need 3 beams. Does everybody see why we had to subtract one? So now then we're looking at posts. The posts are spaced 16 feet apart along those beams. So there'll be one at 16 feet, 32 feet, 48 feet, and then of course 64 feet would be the wall. So it's the same type of thing there. Each beam needs posts. So the posts on each beam . 64 feet of run divided by 16 feet of spacing is 4 again. But once again, we don't need a post at the beginning or at the end, so we subtract 1. That is 3 posts per beam. So our total posts, we have 3 beams times 3 posts per beam, gives us 9 total posts that are going to be needed. Oh, I can't write today. There we go. So that's an important concept in construction and any sort of spacing problem. If you don't need them at the ends, you divide out the length by the spacing and you subtract 1. Now in this next problem, it's going to be the opposite. Here we have a 96-inch wall. So this wall runs 96 inches. And we have studs that are going to be spaced 16 inches on center. So we'll have one here at 16 inches, 32 inches, 40, oops, I drew those way too, yeah, we'll make it work. 48 inches, 64 inches, 80 inches, but I do need one at the end here. I need one at 96 inches, but I also need one at the beginning, at the start, yes. If I did 96 divided by 16, I'm just going to get 6. And just like over here in this first example, that gives me all the ones in the middle plus the one at the end, but it does not give me the one at the beginning. So in a case like that where we do need them at both ends, we would have to add 1 to that. So it's going to require 7 studs to build that wall. Does that make sense? You work with, studs is a big one where you're usually going to be adding 1. Roof trusses are the same thing. You have your spaces, depending on whether you're using gable trusses or just using standard trusses on the ends. If you're using standard trusses, you're going to divide it out and add 1. If you're using gable trusses, you're going to divide it out and subtract 1 because you're going to have you won't need them at the end. You're going to have the special trusses at the end. Do you have a question? Yep. Yeah, generally you need, yeah, for rebar it's the same thing. You have to have an extra one at the end. I did a lot of concrete for years, and rebar is a tough one to figure because you got the bends and the bending loss and overlaps. I worked on the county watershed projects, so you have to, all the engineering into that. You have to have 18-inch overlap between rebars, and at least 3 ties per overlap. You know how that works, don't you? Yeah, the 6 is it's yeah, 6 is a 6/8. A number, because most of what we did was a number 4, it was 1/2 inch, 4/8. Yep. Well, for stuff that's vertical, if you have any walls, those usually use a number 6 bar. I always liked working with a 3, just the 3/8 bar bends. You can bend that by hand. The number 4, the 1/2 inch, I always took 2 pipes and usually a post hole in my post pocket in my trailer to bend them. But the number 6, the 3/4 inch, you have to have a bender to do that. Or a torch. They kind of frown upon you heating up rebar. Okay, so there's some other concepts here that construction related with the math we've already done that I want to make sure you guys understand. Let's talk a little bit about stairways. So we have story to story height. It's usually called just story height. Is the distance from the top of one floor surface to the top of the next floor surface. Obviously, stairways go from one to the other. If I have a typical riser is 7 inches tall, so the riser is this height right here, 7 inches. If that typical riser is 7 inches tall, let's say we have, what do I want to do here? Let's do 126 inches for my story height here, from one floor to the next. How many risers do I need? Okay, how'd you get that? Perfect. 126 divided by 7 gives us 18 is correct. Now, how many treads or runs is that going to end up being? You would think it would be 18, wouldn't you? It's 17 because you have a rise on top and a rise on bottom. You always get one extra rise. So it only takes 17 treads or 17 runs. That one always gets me. I go back and forth between the architectural design program and the woods program. In architectural design, you call it a unit run. And in the woods program, they always refer to it as a tread. So if you hear me say unit run, that's what I'm referring to as the tread of a stairway. It's just a unit run and unit rise are the technical terms for it. They use the same, like I saw you had a roof slope up here. And technically, you're not talking, they use the term pitch for roof. They call it a pitch. It's not a pitch. It's a slope. We'll get into that at some point too. They call it your unit rise on your roof. A 4-inch unit rise, that means it's a 412 slope. It's just a technical term they use for it. I don't know, it makes the engineers feel important, I suppose. Let's say we have a 25-foot by 80-foot roof. Just a single plane, we don't have to worry about slopes. That is the actual dimensions of the surface. The area of that, how do we find its area? Perfect. 80 feet times 25 feet. Well, 80 times 25 is 2,000, but we also have to do feet times feet, is square feet. The symbol you guys might run into, by the way, you guys know the single quote, of course, is the foot symbol. That's the foot symbol with a square around it. A lot of architects and engineers use that as their symbol for square feet just to write it out quicker. It took me a lot of years when I started teaching to get away from doing that because all my students would look at me with a weird look on their face when I did it. But you will see that symbol from time to time as square feet. Of course, that's inches, that's square inches. Anyway, in construction and architecture, we don't usually refer to things as square feet, we refer to them as a square. Does anybody know what a square is? A square is 10 foot by 10 foot, or 100 square feet. When we talk about roofing, they look at a cost per square. You might hear somebody bid a roofing job and say it's going to be 28 square. That's what they're talking about, is 28 10 foot by 10 foot sections. Well, all that means is you're going to take your area of 2,000 square feet and divide it by 100. So 2,000 divided by 100 here is just going to give us 20 square. Shingles and siding are the two big things that are bid in squares. So the same thing, if you figure out your surface area for your siding, you're going to add your waste factor, you're going to divide by 100 and quote it as a square. I think that's all I had for stuff I wanted to make sure I went over. Does anybody have any questions off the homework from Monday? We're good? Okay. Well, it is unfortunately that time for a quiz again. So I'll hand this out for you. I do have your quiz from last week. We'll get back to you here. Did they talk to you at all this week? They talked to you at all this week? They just had you officially registered for the workshop. So they're going to be coming to you to get you to do Now I just gave you quiz 1 back. So now that you have your first quiz back, I want to explain a little bit about what to do with it now. It's not necessarily done. I allow you to do corrections. All corrections are is going back for the problems you have incorrect, redo them, and then make sure you show your work. I don't usually require you to show your work on the quiz, but when you do corrections, I do want to see your work because I want to make sure that you have the correct process down and didn't just find somebody with the right answer and write it down. I do these for 2 reasons. I want to make sure that you do have that process or seen the process to do it correctly, and to give you some points back. You do get half your points back. So even if you had a 9 out of 10, that's a 9.5. There are roughly, well, there will probably be close to 14 or 15 quizzes this semester. So that even if it's a half a point per quiz, that's 7 or 8 points. That adds up in a hurry. So I recommend you do them. You can get help. You can work with each other on them if you want to. If you still can't figure them out, you can ask me. I'll be happy to take class time and work through problems if you need me to. Like I said, it's very important to me that you have the correct process down and to get as many points as possible. I don't want to see anybody fail if we can possibly avoid it. So. Is anybody looking over that quiz? Does anybody have something they're just absolutely stumped on? The big ones on the first quiz were 3 and 5 were the ones that a lot of people got wrong. 3, most people that had it wrong were a little bit short on their calculation. Most people were 4 feet short. I'll tell you flat out, the answer on that is 68. So if you search through and find, so for work on that, just list out all the links that you would add together. Most of you are missing a 4-foot piece somewhere, probably on the inside of that sidewalk. And then number 5, most people that had that wrong also listed that as 8 feet. So I'll give you a hint. The correct answer is not 8 feet for number 5. That is a tough one because you have to, you have not all the dimensions are going building up. Some are adding and some are subtracting for that one. So if you have any issues with that one, let me know and we will do that one together at some point. Yeah. You have an issue with that one? Okay. Let's get her out of the way then. The first thing you have to work with is the fact that I don't draw to scale on my quizzes. I do that for 2 reasons. One, because drawing to scale is really tough on a computer screen when you don't have an architectural program, which I don't when I draw these out. I'm just doing basically hand sketches in Word. And also, I want you to trust your math and not just the drawings. So on this one, a lot of people saw that this is 8 feet here, and they appear to kind of line up, so they kind of just assume A is going to be 8 feet as well. That doesn't turn out to be true. So I'm only going to label the vertical dimensions here because those are the only ones we need to find this. One of the strategies we can use is to use a reference line. And since A is a vertical dimension, I draw a reference line horizontally. And it's nice if I can do it next to A, and since it does touch the bottom here, my reference line is going to go across the bottom. So all I need to know is the distance from my reference line to the other end of A, and I have that length. So let's establish that length. If we call this reference line 0 feet, up to here is going to be how far away from the reference line? 28 feet, good. Of course, this is horizontal, so it doesn't change that at all. This is still 28 feet. How far is this going to be? 36. We add another 8 feet to that. How about here? Still 36. Right? That's flat across. Going up to here, how far? 42. Good. Now we got to start coming back. This is still 42 feet. How far is this going to be? Minus 30 will be 12. Good. And then here, 2 feet. So this is 2 feet away. Oops, 2 feet, not 21. We go back up to here. That's going to be at 10 feet. So this will be 10 feet. So A has to be 10 feet long. Yeah, don't trust my drawings. I will warn you, I don't do things to scale when I sketch these out. Any others that anybody is totally stumped on? Okay. As you're working through them, if you run into something that you're stumped on, that's fine. Um, these corrections, if you can get them back to me next Friday in class, if you don't have them done by then, I can help you with them, get you finished up on them. Like I said, half your points back, that makes a big deal by the end of the semester. Okay, so our next topic, we finished up fractions. The next logical topic is to talk about decimals. Now, decimals are a lot simpler to do the calculations on, so we're not going to spend a lot of time doing the calculations, but I do want to spend a little time talking about the structure of decimals and where they come from. Just like our whole numbers, place value plays a huge role in our decimals, and it's one of those where a lot of people have never seen the real meaning of the place value with the decimals. So let's go back to our place value with our whole numbers quick first. This is the ones, tens, hundreds, 1,000s, 10,000s, and building up. And I purposely wrote those out as numbers so that we can see the pattern here. Every time we move one place to the right, that place value is divided by 10. 100,000 divided by 10 is 10,000. 10,000 divided by 10 is 1,000. 1,000 divided by 10 is 100. 100 divided by 10 is 10. And it keeps going. 10 divided by 10 is 1. Well, this pattern continues on the right side if we go past the decimal point. 1 divided by 10 is a tenth. A tenth divided by 10 is a hundredth. Divided by 10 is a thousandth. Divided by 10 is a 10,000th. And divided by 10 again is a 100,000th. Now, as you're looking at those place values, you might be thinking that those look suspiciously like fractions, because that's what they are. Decimals are nothing more than a shortcut way of writing very specific fractions. In fact, they're usually referred to as decimal fractions. All they are is fractions that have denominators that are powers of 10. So if I have a decimal like 0.68, that literally means 68 is my numerator, and my denominator is the place value of the last digit. That 8 is in the hundreds place. That is, we would pronounce that as 68 hundredths, but it literally means the fraction 68 out of 100. In fact, it's that simple to convert a decimal into a fraction. Now, of course, we wouldn't leave it as 68 over 100. What can both of those be divided by? 2 would work. 68 divided by 2 is 34. 100 divided by 2 is 50. Are we done? No, we can still divide by 2. Perfect. We get 17/25. Now, there are a ton of flies in here today, aren't there? I was actually thinking about going downtown and grabbing a fly bomb, but I figured anybody has allergies, it's probably not a good thing to be breathing in poisonous gas. You have allergies to fly bombs? Yeah. I'm kind of surprised they are sticking to the window, but that's the other thing is I figured if I sprayed them, they'd get sticky and they'd be landing on everybody. So if we want to do, let's do one more example of converting one of those decimals to a fraction. Let's do this one, 5.0375. Now this one, of course, I have a number in front of the decimal point. That decimal point is what separates the whole number from the decimal or the fraction portion. Just like with our fractions, we have mixed numbers. This is also a mixed number. The 5 is a whole number. That's going to stay. That does not change. The 0.0375 is what gets converted into the fraction. That is 375 over 10,000. There we go. It's tenths, hundredths, thousandths, 10,000ths. A way to double check yourself. I hate doing gimmicks, but this is one of them that's worth it. There are 4 decimal places there in the decimal. There's 4 zeros in the denominator. Now, of course, that can be reduced. Both of those can be divided by 5 will work. So what does that give us? 75 over 2,000. Both of those can still be divided by 5. You could have divided by 25. You're correct. Yes. So 75 divided by 5 would be 15 over what? 400. And then they can still be divided by 5. Give us 3 over 80. Yeah. Yeah, we could have divided by 25 here or here yet to get to 3/80. So that is 5 and 3 over 80. Towards the end of our decimal work here, I'll actually show you a process. This is converting it to an exact fraction. Which is fine for now. Working with the actual math side of it, the numbers, that's how we usually would do it. But in construction, we don't usually care about 80ths. Typically in construction, depending on what you're doing, you care about 8ths or 16ths. So we'd be looking at how would we convert it to the nearest 8th or nearest 16th, rather than the exact fraction like that of 3/80ths. So let's look at some of our operations here. We've got a couple minutes left before break time. So let's look at addition and subtraction. Remember, when we add and subtract, we need the same name. With whole numbers, that was lining up the place values. With fractions, that was the common denominator. With decimals, that is lining up the decimal points. And then, of course, as with any form of number, we're going to combine the counts. Come on. And then we are going to keep the same name. How we keep the same name with decimals is just going to be to drop the decimal point down. So let's do a couple of examples real quick. So we might have 0.78 plus 0.049. So when I go to add these, I'll write the first one, the 0.78. Before I write the second number, I usually just put the decimal point in so it's lined up, and then I fill in. So 0.049 would be like that. And if I line up my columns carefully, I can see that I have a spot here that I'm going to fill in with a 0. I had an extra decimal place in the bottom number, so I have to fill something in on top to balance that out. And now I'm just going to add, just like the decimal point isn't there. 0 and 9 is 9. 8 and 4 is 12, so it's 2 carry the 1. 1 and 7 is 8, and I'm at my decimal point. So I bring the decimal point down. There's nothing to the left, so that's it. If I have something like 27.835 plus 9.68, same type of thing. I'll write my first number. Then I usually put my decimal point in for my second number first. Now I'm going to work out in both directions. I got the 9 here, the 0.68. There we are. Now I still have to fill in that missing digit on bottom this time. And then we add. So 5 plus 0 is 0. 3 plus 8 is 11. So again, we'll keep the 1, carry the 1. 1 and 8 is 9, plus 6 is 15. I'm going to keep the 5 and carry the 1. Notice the decimal point does not affect that carrying at all. Yes, sir. Yeah, it would be. Thank you. It's definitely Friday afternoon. Sorry. Yes, it would be 5. Thanks. So 5 plus 0 is 5. 3 plus 8 is 11. So 1, carry the 1. 15. Notice the decimal point does not affect our carrying the 1 there. But before I can add that next column, I do have to bring my decimal point straight down. 1 and 7 is 8, plus 9 is 17. So again, we keep the 7, carry the 1, and 1 and 2 is 3. So we got 37.515. Any questions there, other than why I can't add? Okay. It is 2:21, so it is break time. Let's keep rolling here. So, subtraction. Our subtraction follows the same rules as addition. So we have to have the same name, lining up the decimal points, and combining our like place values. So we're going to look at something like 2.34 minus 0.728. So we have to make sure we line up that decimal point again. So I'm going to write the first number, and I'll put my decimal point in for the second number, 0.728, and we are subtracting. And of course, just like our addition, we have to fill in those missing place values with zeros, and then we'll subtract. 0 minus 8, well, just like whole numbers, we'll borrow. That becomes a 3 and a 10. 10 minus 8 is 2. 3 minus 2 is 1. 3 minus 7 can't be done. So we're going to borrow from the 2. That'll be a 1. This is a 13. Notice that the decimal point did not affect our borrowing at all again. 13 minus 7 is 6. We drop that decimal point straight down. Of course, 1 minus nothing is just 1. The one example I wanted to make sure I showed you looks something like this. 13, decimal point out, 13 minus 7.6384. So first of all, in the 13, where's the decimal point? After the 3. If the decimal point is not written in, it's implied to be at the end of the number. So that's what we have to line up with our decimal point in the second number. Now we have several places to fill in here. In fact, we have 4 decimal place values to fill in with zeros. And when we go to subtract here, 0 minus 4 can't be done, so we need to borrow. But there's nothing here to borrow from. So we keep going until we find something that has a value to borrow from. That would be the 3. Now when we borrow from that 3, it becomes a 2. That makes this a 10. But we need it down here, so we have to keep borrowing. Borrow from the 10, that's a 9, this is a 10. Borrow again, that's a 9, this is a 10. One more time, that's a 9, now this is a 10. A lot of you are probably trying to shortcut, you borrow and then just do 9, 9, 9, 10. That's what's really going on, is you're just borrowing repeatedly until you move over to where you need it. So now 10 minus 4 is 6, 9 minus 8 is 1, 9 minus 3 is 6, 9 minus 6 is 3. Drop the decimal point down. 2 minus 7 can't be done, so we borrow, that's a 0, this is a 12. 12 minus 7 is 5. Any questions? So now remember, when we multiply and divide, we do not need the same name. So that means that when we multiply or divide our decimals, we don't have to worry about lining up decimal places. Of course, we're going to combine counts like we do with every operation. And then we also combine the names. So we'll have to look at strategies for combining names when we do each of these. So let's look at multiplication. Let's do 2.83 times 0.64. Now we don't need to line up the decimal points. In this one, they just happen to line up for us, but it doesn't matter. We're going to completely ignore those decimal points as we do our multiplication. So just like with whole numbers, we start on the bottom number and the last digit. 4 times 3 is 12, so we'll keep the 2 and carry the 1. 4 times 8 is 32, plus 1 is 33, so we keep the 3, carry the 3. 4 times 2 is 8, plus the 3 is 11, so 1. No place to carry the 1, so we'll just move it over. Now when we move over to the next digit, we're talking put in a 0 down here. I always put a line up there as well to make sure I know those are old carries. 6 times 3 is 18, so 8, carry the 1. 6 times 8 is 48, plus 1 is 49, so 9, carry the 4. And 6 times 2 is 12, plus 4 is 16, so 6, and we move the 1 over. That's all we have for digits there, so we're going to go ahead and combine them. 2 and 0 is 2. 3 and 8 is 11, so 1, carry the 1. 1 and 1 is 2, plus 9 is 11, so 1, carry the 1. 1 and 1 is 2, plus 6 is 8, and 1. Now, where do we put the decimal point here? Right there, between the 1 and the 8. And of course, the reason why what we've been taught is you have to count 1, 2, 3, 4 total decimal places in the problem. You start at the end, count backwards, 1, 2, 3, 4 decimal places in our answer. Also, if you look at it, this is about 3, that's about 1. 3 times 1 is 3. We're expecting an answer close to 3. Well, 18.112 wouldn't make any sense, and 0.18112 would not make any sense. So that's the only place that really makes sense to put that decimal point. Realistically, I realize decimals are really simple to enter on the calculator. I use the calculator for most of them myself. The big thing is on a lot of calculators, the decimal point doesn't appear until you punch in the next digit. So you're never really sure if it registered or not. So like what I did here of, okay, I'm expecting it to be close to 3. Having that in the back of your head helps so that if this spits out 181, you know something went wrong. You know the decimal point didn't register when you entered it in. Division, just like with our other operations, division is the one operation that's been mutilated the most. If I take something like, let's do 78.54 divided by 2.1. As we saw back in our first day, what we're really doing when we do division is we're taking place values to create big bundles to subtract from that number. Here, that first place value is the tens place. We do 10 times 2.1 is 21. I can subtract that. In fact, I can subtract it 3 times. 21 times 3 is 63. I subtracted that of 15 left over. So I had tens. I did it 3 times. 10 times 3 is 30. And we could go through the place values like that. Well, that's not how we've been taught to do it, is it? We've been taught shortcuts. So what we've been taught is to not divide by a decimal. Instead, we've been taught to move that decimal point over to make that 21. But what else do we have to do when we do that? Yeah, move the decimal over in the other number once. We moved it 1 spot here, we have to move it 1 spot here. That becomes 785.4. The reason we're allowed to do that is fractions and division problems are kind of interchangeable. We can think of this as 78.54 over 2.1 as a fraction. And now to get rid of that decimal down there, I would multiply by 10. 2.1 times 10 is 21. But if I multiply the denominator of a fraction, I have to multiply the numerator by the same thing. So 78.54 times 10 is 785.4, which is exactly what I have right here, 785.4 divided by 21. Now our division proceeds just like it would for whole numbers. 21 does not go into 7, so I'm going to leave it blank above the 7. 21 goes into 78 3 times. 3 times 21 is 63. We subtract, we've got 15 left over. We're going to bring down the next digit of the 5. 21 goes into 155 how many times? 21 times 7 is 147, so we'll go in there 7 times. We subtract, what do we have left over? Perfect, 8. Now before I bring down the next digit, what do I have to do? Yeah, I'm crossing the decimal point, so I gotta move the decimal point up. Now I can bring down the 4. 21 goes into 84, 4 times. So that's 37.4. Now, what if it doesn't divide out nice and evenly like that? That one ended after 1 decimal place. That's a pretty nice, simple division. There we go. So I have something like 42.63 divided by 3.2. So the first thing I'm going to do is move the decimal points. There's only one place value here, one decimal place there, I should say. So I only have to move it 1 spot each. So that becomes 426.3 divided by 32. 32 goes into 42 once. We subtract, there's 10 left over. We'll bring down the 6. 32 goes into 106 3 times. That's 96, so there's 10 left over. Before I bring down the 3, I have to take up the decimal point. Now I bring down the 3. 32 into 103. Still 3 times. That's 96. There's 7 left over. Now let's say I should tell you that I want this answer to the nearest thousandth. But we're only at the 10th here and we've run out of places. But as you said, we can add zeros. So add a 0 and bring it down. 32 goes into 70 how many times? Twice. 2 times 32 is 64. So we subtract, we have 6. Add a 0, bring it down. 32 goes into 60. Once. 1 times 32, of course, is 32. There would be 28 left over. Now we're at the thousands place. Does that mean we're done? Not quite. Remember, to the nearest thousandth implies that we're going to be rounding it to the thousandths place. To round it there, we need to know what the next digit is so we know whether we keep it the same or round it up. So we're going to add 1 more 0 and bring it down. Well, 32 goes into 280 8 times, I believe. 8 times 32 is 256. So yes, that is correct. There's 24 left over. So what this is telling us is to the nearest thousandth, which is that digit, that 8 is telling us it has to round up to 13.322. So you always have to go 1 digit past. Now, of course, I realize that many of you are going to do this on the calculator, so you just have to read it to that digit and round it off. To be honest, about 4 times a year, I do long division by hand like that, and that's to show it to a class. So I use the calculator on those if they come up myself. So now with that practice, with that procedure in there, we can look now at converting a fraction back into a decimal. We all know that 3/4 is what is a decimal? 0.75. But if we didn't know that and we had to divide, we would do, remember, a fraction is a division problem. 3/4 is 3 divided by 4. Well, 4 doesn't go into 3, so we've either got to leave it blank there or put in a 0. And since there's nothing left, I have to put in a decimal point. We'll bring that decimal point up. The reason I have to put in the decimal point is I can only add zeros to a number after the decimal point. So I put in the decimal point so I can add a 0. 4 goes into 30, 7 times 4 is 28. These are the 2. We'll add another 0 and bring it down. 4 goes into 20, 5 times. So 0.75 or 0.75, whichever you prefer. We might have 5/16. That's going to be 5 divided by 16. Well, 16 does not go into 5, so we're going to put in the decimal point, bring it up, add a 0. 16 into 50? 3 times. 3 times 16 is 48. So we subtract, there's 2, add a 0 and bring it down. 16 into 20? Once. That's 16. We have 4 left over. Add a 0 and bring it down. 16 goes into 40 twice. Good. 2 times 16? 32. That's 8. Add a 0 and bring it down 5 times. 5 times 16 is 80. So there we go. We already looked at the beginning of class converting a decimal into a fraction. 0.5625. If I want to convert that, I'm going to label as inches, to an exact fraction. We do exactly what we did at the beginning of class. That's 5,625 over 10,000. Good. Tens, hundreds, thousands, 10,000s. 4 decimal places, so 4 zeros. Both of those can divide by 5, but they can also divide by 25. So let's start with that. This is going to be, what, 225, and that'll be 400. Both of those can be divided by 25 again. If you didn't see the 25 and divided by 5s, you just have more steps. You'd still get the same spot. 225 divided by 25 is 9. 400 divided by 25 is 16. That is 9/16. Well, that came out to a 16th. But if it didn't, if I have something like 0.71, we'll make it a little bit more useful, 712, which is 712 thousandths, as I reduce that, both of those can actually be divided by 4. Well, 712 divided by 4 is what? 178 over 1,000 divided by 4 is 250. Don't have that drill size in the toolkit, do we? In construction, we don't care about 250ths. We care about 16ths, 8ths, quarters, halves, 32nds, and 64ths if we want to get fairly precise. 250ths don't work for us. So rather than converting it to an exact fraction, we might be asked to convert 0.712 inches to the nearest, bless you. What's that? It could still be reduced by 2. You are correct. Yeah, that could still be 89 1/25. Still don't have 1/25 in the toolkit. If I want it to the nearest 16th of an inch, it is a totally different process. Looks nothing like what we did to go to the exact fraction. What we're going to do is we're going to make this a fraction in the simplest way we know how. 0.712 over 1. We can make anything in a fraction by just putting it over 1. Notice the decimal's still in there, by the way. That's the biggest mistake people make, is they pull the decimal out. It's still there. We haven't put any big numerators underneath or denominators underneath it to change that yet. This has a denominator of 1. We want it to have a denominator of 16. So how are we going to change it? Multiply by 16. 1 times 16 is 16. 0.712 times 16 is 11.392. So what this is telling us, the 11.3, is telling us that we are between 11/16 and 12/16, or 3/4, yes. Which one are we closest to? The 11.3 says we're closer to the smallest one, 11/16. So to the nearest 16th of an inch, that is 11/16. We might have something like 2.39 inches. We want it to the nearest 32nd of an inch. Well, first of all, the 2 in front of the decimal point, that's whole inches. We don't need to worry about that. We got 2 whole inches. It's the 0.39 that we have to convert. Once again, we convert it by putting it over 1. This time, however, we want the denominator to be 32. So we're going to multiply by 32. 1 times 32 is 32. 0.39 times 32 is 12.48. So that's telling us that we're between 12 30-seconds and 13 30-seconds. We're closer to the 12. Now 12 30-seconds, of course, can be reduced by 4. 12 divided by 4 is 3. 32 divided by 4 is 8. That's 2 3/8 inches. Now I get people ask me all the time, well, why did you change that to 8s? I thought you said you wanted it to the nearest 32nd. Well, 3/8 is 12 30-seconds. It's to the nearest 32nd, it's just been reduced. So even though they say to the nearest 32nd, it's still okay to reduce it if you can. It's much better to reduce it if you can. I'm gonna have you guys try a couple here. Let's have you do 0.593 inches to the nearest. Let's have you go to the nearest 64th of an inch with that one. And 3.91 inches to the nearest 8th. Let's see how you're doing on these. So the first one, 0.593 inches, we'll put 0.593 over 1. What are we going to multiply by? 64. We want 64th. So 0.593 times 64 is 37 point what? Okay. So that is between 37 and 38. It's going to be closest to 38/64, which reduces to 19 30-seconds of an inch. Good. This one, we're going to keep the 3. 0.91 over 1. What are we going to multiply by? We want 8, so we're going to multiply by 8. Good. So 1 times 8 is 8. 0.91 times 8 is 7.28, correct? Between 7 and 8, what's it closer to? 7, 7/8. So we can't forget our 3, that's 3 7/8 inches. What if I had something like 0.96 inches and I wanted it to the nearest 8th? Well, that would be 0.96 over 1. And I would multiply by 8 on top and bottom again. 0.96 times 8, however, is, what is that, 7.68? Well, that's between 7 and 8. It's actually closer to 8 eighths, or 1. You're exactly right. So we would call that 1 inch to the nearest eighth. Okay, so that is it for the decimal part of it. Our next step is to move on to one of the more powerful tools in math, actually a small piece of the more powerful tools in math. One of the most powerful tools we have in math is the concept of ratio and proportion. And we will use those later on in the course. For those of you, if any of you go on to WITC, the second math class in the Woods program, in the construction program, is pretty much all about ratio and proportion. All your trigonometry and stuff is ratios. And we're going to, it's basically a geometry class of comparing shapes and finding missing dimensions and all that stuff. It's all ratio and proportion. Today we're going to focus on, or for the last few minutes here, we're going to focus on one application of ratio and proportion, and that is a percent. To understand how percents work, we need to understand the word percent. It's actually two words, per, if you think of miles per hour, miles per gallon, dollars per hour, it's like for each or out of. And cent, if you think of years in a century, cents in a dollar, it means 100. So percent literally means out of 100. So if I have 36%, that literally means the ratio 36 out of 100. A lot of people refer to that as the fraction form of a percent. It is a fractional form. It's not a fractional percent, because a fractional percent would still have this percent sign after it, but it is a fractional form of the percent. Technically, though it's not a fraction, it is a ratio. That isn't 36 hundredths, that's 36 out of 100. There's a very slight difference, very subtle difference between those. However, I can still reduce this just like I would a fraction. Both of those can divide by 4, which would give me 9/25. There we go. 36 divided by 4 is 9. 100 divided by 4 is 25. We might have something like 85%. If I want to put that in that fractional form or a ratio, it's 85 over 100. What can that be reduced by? 5, which would give us, could somebody say it? There's 17 over 20. Perfect. Well, it's not always that easy. We might have 244%. That is still just 244 out of 100. You'll see if you think of that as a fraction, that's an improper fraction. I know there's a couple of things that need to be done. It needs to be converted to a mixed number. It also needs to be reduced. I usually convert it to a mixed number at this stage because dividing by 100 is pretty easy to do. How many times does 100 go into 244? Twice, with how much left over? 44. Can't ask for an easier conversion than that one. Now we can reduce the 44 and 100 by 4. Good. 44 divided by 4? 11/25. Good. And we got to remember the 2 there. So 244% is 2 and 11/25. One of the things I mention when I do percents is the word benchmarks. One benchmark is 100%. 100% means the whole thing, or 1. This is bigger than 100%. It's going to be larger than 1. We might have something like 36 2/3%. Well, again, that still just means 36 2/3 out of 100. We do not like having fractions within our fractions. We have 2 possible methods we can get rid of it. One is to treat them as 2 separate numbers and think of least common denominators. Well, the only denominator here, if we separate those, is the 3. So I can multiply both the top and bottom of that ratio by 3. Well, 100 divided by 3 is 300. That part's pretty simple. Or not divided by, multiplied by 3. 36 2/3 times 3 is a little trickier. We have to make the 36 2/3 into an improper fraction. 36 times 3 is 108 plus 2, 110. That's 110 thirds times 3 over 1. 330 over 3. And of course, you can divide out the 3's to get 110 over 1 or just 110. Right? So it's 110 over 300. Both end in 0. We'll divide by 10. It's 11 out of 30. So 36 2/3% is equivalent to 11 out of 30. We might have 56.25%. Oops, I forgot to show you the second way. Sorry, the second way we can reduce this here. I can actually just treat it as a division. 36 2/3 over 100 is 36 2/3 divided by 100. I make that 100 over 1. 36 2/3 we already said is 110 over 3 times 1 over 100 is 110 over 300. Both of those divide by 10 again. Gives 11 over 30. I think this is simpler to just divide it with the fractions than it is to try to do that common denominator. All right, let's go back to that 56.25%. That is still just 56.25 over 100. Well, just like we don't like having fractions within our fractions, we don't like having decimals within our fractions. Some of you might notice we could multiply by 4 and get rid of that. That would give us, what, 225 over 400. If you don't see that, though, we can always, there's a method that'll always work, just like we did when we were dividing our decimals. There's 2 places here. I can multiply by 100 to move the decimal point over 2 places. That becomes 5,625. 100 times 100 is going to be 10,000. Now it's going to be a little bit ugly to reduce. Both of those can be divided by 5 or 25. There we go. We divide by 25, that is 225 over 400. If we'd have multiplied by 4, we would have skipped right to that step. It would have saved us a little bit of work. But again, you don't always see that. We can divide by 25 again. 225 divided by 25 is 9. 400 divided by 25 is 16. 9/16. So 56.25% is the same as 9 out of 16. Yeah, we've used that number a couple times, yeah. Let's have some, well, let's convert to a decimal form. Now I say decimal form, a lot of people say just decimal because it's technically not a decimal. 36%, as we said, means 36 out of 100. To turn a fraction into a decimal, we could simply divide 36 divided by 100. When we divide by 100, it just moves our decimal point back 2 spots. That's 0.36. Like I said, most people refer to this as the decimal form of a percent. It actually has a name. It is called a rate. So we're converting it to the equivalent rate. Anytime we convert a percent into a rate or a decimal, we're dividing by 100, which means we're just moving that decimal point over 2 spots. So 71% is going to become what as a rate? 0.71. 210% will become what as a rate? 2.1. Good. 8% will become what as a rate? 0.08. Good. 3.2% will become 0.032. Good. 0.7% will become, there we go, 0.007. Good. Here's the one a lot of people miss. 1/4% becomes, a lot of people want to say 0.25. That's still a percent. Just move from a fractional percent to a decimal percent. To get it to the rate, we still have to divide by 100. There it is, 0.0025. I mentioned the word earlier called benchmarks. One of our common benchmarks is 1%. 1% as a rate is 0.01. 0.7% is smaller than 1%. Its decimal better be smaller than 0.01. 1/4 is smaller than 1%. Its decimal better be smaller than 0.01. So that's one thing we use. We use those benchmarks to estimate, to catch some of those mistakes. Now, if I want to go from a rate back to a decimal, if I have 0.35 as a rate, that means a rate means out of 1, 0.35 out of 1. Of course, our rate back to a percent means out of 100. So all we're really doing here is multiplying by 100, which moves the decimal point back. So that's 35 out of 100, or 35%. So to go from our rate or decimal back to a percent, we're just moving the decimal point the other direction. So 0.76 becomes what is a percent? 76%. 0.2 becomes 20%. 0.075 becomes 7.5%. 3.6, careful, 360%. Good. 0.008, 0.8%. Our last step is to turn our fractions back into percents. Let's start with one, just like we did with our decimals that we know. We know that 3/4 is what percent? 75%. If we didn't know that, we could have turned 3/4 into a decimal by doing 3 divided by 4, which is 0.75. And then, of course, we move the decimal point, make that 75%. Not all of them work out quite that neatly, though. So the other way we could look at it, 3/4 is really 3 out of 4. A percent is out of 100. This is one where we know that we can multiply 4 by 25 to make 100. So 3 times 25 is 75. 75 out of 100, or once again, 75%. But like we said, they don't always work that simple. So if we run into something like 5/8, 5 out of 8, and we want to know what that is out of 100, it's not so easy to see what we would multiply the 8 by. What we would do to find that is we'd do work backwards. We do 100 divided by 8, which is 12.5. So that means we would multiply the 5 by 12.5 to get 62.5. Or 62.5 out of 100, or 62.5%. This leads us to a shortcut. What we really did there, we took that 5 times 100 divided by 8. Oops, divided by 8. Well, and this happens long enough that the shortcut that's developed, or the strategy that's developed, is we notice the two numbers that are diagonal with each other get multiplied, 5 times 100. The other number that's diagonal with the missing piece, we divide by. So if I have 2/5, 2 over 5, equals blank over 100, the two numbers that are diagonal here are the 2 and the 100. I'm going to multiply those. 2 times 100 is 200. The 5 is a diagonal with the missing number. I'm going to divide by that 5. 200 divided by 5 is 40, so that's 40 there. 40 out of 100, or 40%. Any questions? Okay. So we got homework out of the little book. It is units. Eleven, 12, 13, 14, and 15. The odds. We will talk more about percents on Monday. You have the last, they've asked me to keep you in here till 3:30 instead of letting you out at 3:20. We'll compromise and do 3:25. Finish up your quiz, get those quizzes turned in, we'll have a few minutes of work and then we'll let you out of here. I had forgotten how uptight high schools are about seat time. Okay, thanks.